continue with the animation lecture. In the previous video, I promised like I'll give a mathematical formulation of the animation that you have seen. So for those who haven't seen, you can just throw the previous lectures of the locus problem, the essence and beauty of locus. So there we have posed a question, like we have an ellipse of a fixed size, where size is, let's say, A and B, and A and B was dynamic, so it was varying. For the sake of solving the problem, I'll take the length of major axis to be 4, so 2A equals 4 and 2B equals 2. As we know, for an ellipse, the major axis is this part, so this entire length of major axis, which is 2A, is given to be 4 and 2B equals 2. By fixing this up, we are basically fixing the size of the ellipse. So we'll get A equals 2 and B equals 1, which is the length of same major and same minor axis. So now the question is, an ellipse of this parameter with A2 and B1 slides on the coordinate axis. Okay, so let's take two configuration, configuration 1 and configuration 2. We'll calculate two locus of two particular points here. One will be locus of center, and other is locus of focus. Okay, so the problem statement is an ellipse having major axis and minor axis as 4 and 2 respectively slides or slips between the coordinate axis in the first quadrant while maintaining the contact with both the axes. We have to find locus of center and the locus of foci of the ellipse. So let's start solving this. We'll start with locus of center first. So to solve this problem, let's take just one particular representative diagram which will speak on behalf of any configuration. So if you have ellipse and some other configuration, clearly we can see this, like center will keep on moving on certain curve. So how to relate the coordinate of the center? So let's say the center of the ellipse in any random configuration is alpha comma beta. So we'll do first part for locus of center, LOC. Now, as we know, what is the guardianship that this ellipse is having? No matter where it slides, x-axis and y-axis is always going to be the tangent to the ellipse, right? So this x-axis and y-axis is always tangential in any configuration. So that is something which is invariant throughout the orientation or throughout the dynamic motion of the ellipse. Now that might give me a guardianship. As we know from the ellipse property, whose videos will be given shortly. So this is a well-known fact from the ellipse that locus of point from which mutually perpendicular tangents can be drawn will lie on director circle, right? So if I'll pick up any point P on the director circle of the ellipse, which is given by x square plus y square equal to a square plus b square. So this is director circle of ellipse. What is director circle? Director circle is the locus of a point from which mutually perpendicular tangents can be drawn to any curve. In case of ellipse, it can be shown, which I am taking it as a ready-made result to solve this problem as of now. The director circle will lie on a circle centered at the center of the ellipse and having radius as square root of a square plus b square. So if you draw any tangents from that circles, magically the tangents will be mutually perpendicular or it will be orthogonal. Okay, so far so great. So we are going to use that property. Since we know like these two tangents are always orthogonal, it means this point, the point of intersection, let's say origin, always lies on director circle. Okay, it lies on director circle of this ellipse, right? And we know the director circle of the ellipse, since it's a circle, so its distance from the center of the ellipse is always going to be constant. Okay, so this r will be constant, and that will be nothing but root over a square plus b square, right? You can visualize this in terms of relative motion. You can imagine as if there is a point P which is moving on this director circle. So with respect to point P, you will look at the ellipse will be seen at 90 degree. Now imagine if you are already on the ellipse, okay? So instead of point P moving, imagine now a frame of reference is attached to point P. So you will feel ellipse moving, right? Ellipse moving, but always it will make an angle of 90 degree. So it's just like basic relative motion concepts in physics. So now question is done because we know this distance is always constant, right? Distance of O from alpha comma beta, no matter what is the configuration of the ellipse, this is going to be invariant, right? This is going to be invariant. And that clearly gives you the locus as alpha square plus beta square, this distance equal to this constant distance square, And now that constant distance square is nothing but a square plus b square. Okay, hence alpha square plus beta square. In our case, a value is 2 and b is 1. So which give 4, 2a square plus 1 square, which is 5. So what's the locus of the center? It's basically a circular arc. In this case, circular arc given by x square plus y square equals 5. Now if you let ellipse move on all the coordinate axes, all the 4 quadrant, then definitely it will give you a full circle. It will give a full circle. If it is fixed only in the first quadrant, then we'll get just an arc of that. So I hope you enjoyed this, and this was quite a basic thing directly coming from the result of director circle. 2 important property of ellipse. So first I'll illustrate the property and then we'll see the logic behind this. The first property is for a given ellipse. Let's say if S1 and S2 is the focus, and we take a random point P, draw a tangent at point P, the photo perpendicular drawn from focus to any tangent. The photo perpendicular drawn from focus to any tangent. So let's say this is tangent t equals 0. From focus on t equals 0, we have a photo perpendicular F1, and from S2 we have F2, right? So this F1 and F2 interestingly will lie on an auxiliary circle. That's magical, right? So F1 and F2 locus will be x square plus y square equal to a square. So this is an auxiliary circle actually, okay? Auxiliary circle to the ellipse. The other property which I'm going to use is not only they will lie on auxiliary circle, not only this photo perpendicular lies on auxiliary circle, but also, so my diagram is not up to the scale, okay? So you have to trust like this point photo perpendicular exactly like on a circle x square plus y square equal to a square, which means photo perpendicular lies on a circle with major axis as a diameter, okay? Not only it lies, but the product of this length S1 F1 into S2 F2, that is going to be b square. What's b square? If you have an ellipse equation, x square plus a square plus y square by b square equals 1. B square is length of square of length of single axis. Yeah. So I'm going to prove both of this result for the sake of continuation of this lecture. Okay. So let's prove first result. If we have got S1 and S2 as 2 focus, let's take up a random tangent t equals 0. Okay. Now the beautifully, if I'll take the image of S1, so let's take the point of contact is P. So I'm going to prove this result for the sake of continuity. Let's take an ellipse having some tangent t equal to 0 to at a random point P. As all of you know, if I'll join from the reflection property S2P, if a ray of light is coming from focus S2, okay. So after reflection at point P, it will go to S1, right? Moreover, S1P plus S2P is always going to be 2A. This is by the definition of ellipse, which follows from focus directrix definition. Now very interestingly, if I take the image of focus, if I take the image of focus in the tangent, so where it will go? Let's say image of focus will go to some point. Okay, it is S1 dash. If I'll take image of focus, it will go to some point S1 dash. Now what if I join point P and S1 dash? Do you feel like this will be collinear? S2P and S1 dash, it will be collinear? Yeah, of course, it will always be collinear. The reason goes like this. Let's say if you have a mirror and we have a point A ray of light starts from point A. Upon reflecting from the mirror, it goes to a point B. Okay. So clearly, you know from the law of reflection, this angle theta will be equal to this. Hence, the remaining angle will be 90 minus theta because this line behaves like a normal, right? So now if someone takes B and reflect it in the mirror, if someone takes B, let's say if you reflect this in the mirror, B dash, you can clearly see like B dash, let's say this point is O and A dash is collinear. The logic is this, since we have reflected, so these two distances are equal, these are 90 degree and this is common, right? So from SAS congruency rule, these two are congruent. Hence this angle must be same as 90 minus theta, right? So what about this entire angle? It's 2 theta plus 180 minus 2 theta, right? This entire angle, theta plus theta 2 theta, and this 180 minus theta. So that becomes 180. And that's something really nice. It means if a ray of light starts from A and it gets reflected to B, if we'll take the image of any point on the refracted ray. Okay, so that image, the point where the ray of light hits and the source of light will be collinear. That's something very remarkable. It's often used in coordinate geometry. So you can clearly see exactly same situation. This tangent t equals 0 behaves like a mirror. We have a ray of light starting from here. Upon reflected, it's going to S. So it can go to any point. And now we are taking the image of focusing tangent line. So now clearly we can see this distance S2P/S1 is collinear. Right? So what about S2S1 dash? What is this distance? It's nothing but S2P plus S1P. Why? Because S1P is equal to S dash P, right? This distance is equal to this because we have taken the image. And that's very interesting because S1P plus S2P is always 2A. So see the magic. It means the reflection of a focus on any tangent is always at a constant distance from the other focus. So this distance is always 2A. So can you guess what will be the locus of S dash? What will be the locus of S dash? Yes, it is a circle with S2 as the center. It's a circle with S2 as the center and 2A as a radius. It's a very remarkable property. If we have got an ellipse, to sum up, we have got, let's say, S1 and S2. The locus of image of a focus in any tangent line will lie on a circle with S2, S1, which is with 2A as a radius and other center as a center of that circle. Okay, similarly you can repeat for other focus. Let's say if you have S2, S1, I take some random tangent. If I take the image of other focus S2, it will go somewhere. And S2 dash locus will be again a circle with S1 as a center this time, with S1 as a center and S1, S2 dash, S2. Okay, now using this property we can find where will be the foot of perpendicular. Okay, so let's continue with this. S1, S2, we have a tangent, let's call some tangent, t equals 0. We have a point of contact. Now what if I'll take the foot of perpendicular F1? So where will be the locus of this point F1? Now clearly we can see, Babu, we can take the image of S1 in that line, it will go to S1 dash. And now we know S1P and S1 dash is collinear. So for the sake of clarity, let me draw diagram properly. Okay, so this is just for the sake of understanding. So S2P S1 dash is collinear and this is already 90 degree, right? So this angle is 90. Let's call that point foot of perpendicular is F1. I've already told. So now can you tell where exactly the point F1 will move? Give a try. Yes, so can you tell where exactly the point F will move? It's super exciting because we have a point F1 which is midpoint of S1 and S1 dash, right? S1 and S1 dash midpoint is F1 and we want to find the locus of this foot of perpendicular. Okay, so we already know we have center C which is midpoint of S1 and S2. What if I connect center C with F1? You might ask like why someone should connect that? Because C is midpoint of the line joining S1, S2. F1 is midpoint of line joining S1, S1 dash. And now we have a triangle S2, S1, and S1 dash. So you are tempted, you are greedy to join them because of class 10 midpoint theorem or Thil's theorem, basic proportionality theorem, right? So what about this distance CF1? What is CF1? It's definitely because of midpoint theorem, CF1 is parallel to S1, S2. S1 dash S2, and not only is parallel but CF1 will be half of S2 S1 dash. And what is S2 S1 dash, Babu? It's same as half of 2A as discussed. So that's something really cool. Why it's so cool? Because C is a fixed point. The center of an ellipse is a fixed point 0, 0. So F1 always moves in a way that distance of C from F1 is A, or F1 is always moving on a path where this distance is constant A. And now you know, because this distance is also A, this distance is A. So what will be the locus of F1? It will definitely be a circle. Because you can tell, let's say F1 is x comma y. So by The distance formula is distance from 0, 0 should be A, so that will be locus as this. And this you call as auxiliary circle. So basically I have proved this because some of you might feel like how exactly geometrically it can be done. Okay, one more result. The consequence of this result which I'll be using is not only the foot of perpendicular drawn from any focus will be on auxiliary circle, but also the product of foot of perpendicular will be BA square. So next target is, if we have got an ellipse, some tangent. Now we have to prove, like we have already shown, like f1 from other focus also. If I'll take f2, so this distance is always okay. The foot of perpendicular always lies on auxiliary circle. So foot of perpendicular lies on the circle x square plus y square equals b square. Surprisingly, this result is also exactly same for hyperbola. Okay, and the proof you can go give geometrically in the same fashion. Now next we'll prove what is the product of this distance. Okay, because I know f1 and f2 lies there. So again, you can basically find distance of a point from this tangent, multiply them, you'll get the answer as in extended textbook. But here I'll give you a crazy method. So let's say this line is having slope m, some slope. So clearly for an ellipse, we can draw two lines having same slope. Like let's start drawing lines. So now no more is tangent, it's cutting it someplace. So we have one tangent of having, let's say, slope equals -2. We can exactly get the tangent having slope -2. Because of a given slope, we'll have exactly two tangents, right? So if this guy has some slope m, we can clearly find another guy on the ellipse having same slope m. Make sense? Now can you see something beautiful from the symmetricity? Because from the symmetricity of the ellipse, so ellipse is placed like this, and you have two tangent lines with the same slope. So they are like parallel track. Okay, so by the center symmetricity of the ellipse, this distance is gonna same as this distance, right? Distance of S1 from this point. Let's call it F1 dash. And S2, and let's call this F2 dash. So this distance is going to be same as this distance. Make sense? So these two distance S2, F2 dash, if we'll draw perpendicular, because anyway these two lines are parallel. For this is 90 degree, and S2, F2 dash is S1 F1, and S1 F1 dash is S2 F2. And that gives a very remarkable way of solving this problem. Because now if I want S1 F1 into S2 F2, basically what we can do, it's same as S1 F1 into, instead of S2 F2, I'll use this length, S1 F1 dash. By using this, what advantage you are having? You are getting a feel of power of a point theorem. Yeah, PA into PV dk square. Because now you have a circle. So we have an auxiliary circle right now, and we have got a point S1. So that S1 F1 and S1 F1 dash. So basically this point will also lie on a circle, right? So my diagram is not exactly up to this scale. So I hope you are getting the feel, right? Yeah, so this is some kind of correct diagram. So we have S1 F1 and S1 F1 dash. So F1 dash and F1 both lie on a circle because of the same property. And now we have a new tangent from focus for the perpendicular line on circle. So S1 F1 into S2 F2 can be written as S1 F1 into S1 F dash. Now what about this into this distance? So clearly you can see we have a circle over here. So we have a circle, and if you have any random point P and a secant cutting it at A and B, and let's say C and D. So from circle we know PA into PB equals PC into PD. This you can prove just by using similarity. Yeah. So it's a well-known result. I'm going to use that. So this into this is going to be, I will take a special distance S1, and let's say this point is A, and S1 and the other point as B. So now we have a circle and we have a chord theorem, bisected chord theorem. We have this distance into this equals this distance into this, right? So you have a circle where these 4 points A, B, F1 and F1 passes on the circle. And you see, now what is distance S1A? So you know distance from center to focus is A, and distance from center to A is A. So S1A will be A minus A. What about S1 F dash? So this guy is same as this guy, right? Anyway, so what about this distance from S1 to B? It's basically A plus A. So into A plus A, and that will give you A square into 1 minus C square, and that's nothing but B square. So this is just two-line proof of this expression, which gives you full feel that not only the foot of perpendicular lies on auxiliary circle, but also their product is length of same minor axis whole square. Now with this two remarkable result, and you have got to learn, so finally we got to learn three things. The locus of image on any tangent to the ellipse lie on a circle with other focus as the center and the radius as 2a. Locus of foot of perpendicular will still lie on a circle with center as the center and radius as a, which is auxiliary circle, and the product of foot of perpendiculars drawn, the product of length of foot of perpendicular drawn is always b square. With these three remarkable properties, now we can solve that locus problem. Okay, so equipped with these tools, we can now solve the problem very comfortably. So let's say we have a particular configuration where we have to find locus of focus. So basically we need to find alpha and beta relation. The given parameter was a equals 2 and b equals 1. If I'll take the image of, now as you can clearly see, we have x-axis and y-axis are always tangent. So we'll use same property. If I'll take image of alpha comma beta in the tangent, which is x-axis, that's going to be alpha comma minus beta. Similarly, image of focus on other tangent is going to be minus alpha comma beta. And we know the image of focus on this tangent will lie on the circle with other focus as the center. So with this as a center, this distance is gonna fixed, right? So that will be 2a. Similarly, this distance is gonna be fixed, that will be 2a, right? So this other focus S1 dash will have a property is that S1 dash with alpha comma minus beta and S1 dash with minus alpha comma is going to be 2a. But now the problem while solving this, of course you can solve this because you know even this distance is 2ae, right? Okay, so since focus S1 dash is still S dash is still variable, so this is not going to help you much, right? So we have to use some other property. Although this might be used in some other problem like this distance is always 2a, but here it's not going to be used. So how will you treat in thought process? So again, let's take if we have ellipse. So the above property is not going to help us much. So let's take an ellipse and this time again focus S1 and S2. Let's put the coordinate of focus 1 as x1 y1 and coordinate of focus S2 is x2 y2. As we have seen in the other approach is x2 y2 and x1 y1. Directly we are not able to get the relation between them. So target is we have to relate, let's say x1 y1. So one of the relation which we already know is the distance between x1 s2, right? So what is s1 s2 distance? That's 2ae. That will give you one constant s1 minus s2 whole square plus y1 minus y2 whole square. That's going to be 4a square e square. So this is constant number 1. Now do you have any other constant? Of course yes, since x-axis and y-axis is a tangent to this, so hence the foot of perpendicular drawn from focus to any tangents will definitely lie on auxiliary circle, right? So this, let's say f1 and f2. Not only this, we know the product of distance s1 f1 into s2 f2 will be b square. Similarly, if I draw perpendiculars to the other tangent, here it's y-axis, so still the length of the product of these lengths is gonna be a square. So we have this distance which is y2 and this is y1. So we have one more constant, y1 y2 is b square. Similarly, x2 and x1 is b square. So coupled with these three relations, now I can easily find the locus of point S. Like we need to relate x1 y1. Now how to relate x1 y1? We know Babu, y2 is b square by y1 and x2 is b square by x1. So how we are going to do that? x1 minus x2 is b square by x1 whole square plus y1 minus y2 b square by y1 whole square is going to be 4a square e square. Now in this particular case, b value was 1 and a was 2. So if I'll put this, x1 minus 1 by x1 whole square plus y1 minus 4 by y1 whole square is 4 into 4 into e square. Now what is e square value? In case of ellipse, b square equals a square into 1 minus e square, implies b square value is 1 is 4 into 1 minus e square, so which gives you e square is 1 minus 1 by 4, which is 3 by 4. So this quantity will be 3 by 4, so we are getting 12. Hence the answer to this problem is x minus 1 by x whole square plus y minus 4 by y whole square is going to be 12. So this is the locus which I was talking about. It will be the locus of focus. Similarly for the other locus also, similarly for the other point also, we are going to get the same locus, right? Yeah. So I hope you enjoyed this, and this is how you solve the problem. Now if someone will ask, like, sir, can we solve the problem using this? Of course it can be done. Let's say this alpha comma beta, it is something or you can take, let's say this is, if someone will ask, sir, can you do the problem using this diagram? So instead of alpha comma beta, let's take this is x1 comma y1 and x2 comma y2. So still you have relations, right? Because x1 comma y1 reflection will be what? x1 comma y1 reflection will be x1 comma minus y1. So you already have one relation between x2 y2 and x1 y1. What is that? x2 minus x1 whole square plus y2 plus y1 whole square is equal to 4a square. Other relation is the distance between them, x2 minus x1 whole square plus y2 minus y1 whole square is 4a square e square. So using both of these relation, and moreover you have one more relation if you want. So using all these three relations, we can easily tell what will be the, you can eliminate basically x2 and x1 and you get the answer. We can eliminate x2, y2. So using these two relations and coupled with one more relation, if I take focus reflection, it will be minus x1 comma y1. So we'll have one more equation, distance from x2 plus x1 whole square and plus y1 minus y2 whole square is 4a square. So we have equation number 1, equation number 2, equation number 3. You can clearly see it's not very tough to manipulate because most of the expressions are equal here. So from first minus 3 if you'll do, you'll get relation between x1 and x2. First minus second you'll do, you'll get a relation between x1 and x2. That is fundamentally you are getting this 2, right, out of solving this. And so this was method 2 of solving the problem, and this was the first method. We'll meet with some more videos on